Hey guys, wanted to put in one little detail here that we need to add about these force diagrams. Sometimes things sit on a ramp or a hill. We call that an inclined plane. Incline, of course, means tilted, and plane means flat surface. So right here is a flat surface that's running up at an angle there. That angle would be theta. It's usually this angle on the ground there. Wouldn't have to be, but generally it is. So we want to talk about these kind of problems, and there's a couple forces and things we want to be able to put in our diagram. So let me remind you here that everything that we're doing is Newton's second law. It's real simple. The sum of the forces equals the mass times the acceleration. We want to use this rule right here for everything that we do. And don't dare look at this over here. All of these problems get worked exactly the same way. You always want to draw the force diagram. So, you know, there's a box, right? And maybe there's a rope pulling up, and maybe there's gravity pulling down, and maybe there's a, you know, whatever's going on. You want to draw those pictures, those arrows. That's the force diagram. And then as soon as you have the force diagram, you want to apply this rule. In this case, I might have F1 and F2. And so when I sum the forces, that would be F1 minus F2 equals MA. And I got myself an equation then. And I need to solve that equation. All right, so let's not worry about that problem. I want to show you how to add the force for inclined planes to that. And so here we go. The inclined plane problem looks like this. I don't know what the question marks are. It's supposed to be a theta down there. Something happened when it went to a PDF. Okay, so that's the angle theta right there. That's that inclined plane that we were talking about. And here's what I'd like you to know about it. When you have gravity pulling straight down and the normal force, the ramp itself, pushing up, those are the two forces on the box. Now I could have a string pulling up this way, or I could have a guy pushing it uphill, or a guy pushing it downhill, or something, but for certain I have gravity pulling straight down, and the normal force is always normal to the surface. It's always perpendicular to the surface. So those are the two forces that I know that I have. And then there could be some others, but they're probably parallel to the inclined plane. And whatever they are, maybe one of them's friction, right? And maybe here there's a rope, and maybe there's a guy in addition to the rope. Maybe there's a rope pulling it uphill, and the guy's along behind pushing it uphill also. Whatever's going on, you've got that. Now what I'd also like you to think about is that this box is going to move parallel to the inclined plane. So my displacement will be either uphill or downhill. And my velocity will be uphill or downhill. And my acceleration will be uphill or downhill. See how everything is running either parallel to the inclined plane or perpendicular to it? And that's only the normal force, except for this guy. Okay? All of the arrows that we've drawn here, including the red ones that were pre-existing, are either parallel to the inclined plane or perpendicular to it. So if I start thinking about the frictional force here, see how it points to the left and down? I've got to break that into components. I've got to get the x and the y component of acceleration and velocity and displacement. That's just a huge mess. The normal force is not either x or y. So we pull a fast one right here. We have a little sleight of hand, a little trick that we pull, and it works out really nicely. Anytime you see something on an inclined plane like this, what I'd like you to do is to draw a new coordinate system for it. And the coordinate system that you really need here would be this. I want the x-axis to run parallel to the ramp, like that. And I want the y-axis to run perpendicular to that. this is going to be the XY coordinate system that I have for this problem right here. And if I do that, we call that a rotated coordinate system. And this rotated coordinate system is really, really nice because it fixes all of that for us. Use a rotated coordinate system. If you see something sitting on a hill or a ramp or an inclined plane, you always, I guess it wouldn't always be true. I hate to use the word always, but generally you want to use a rotated coordinate system. And here's the beauty of it. See how F of F, the frictional force, is now parallel to the plane? It's in the X direction. And the rope and the guy and all my variables of motion, those are all in the X direction. These would be positive X and that would be negative X, I suppose. The normal force is solely in the Y direction. So it fixed all of that, and I don't have to go get the components of each one of those now and treat it separately and make a big mess on my paper. The one that is messed up now is gravity. Gravity goes like that. Since the y-axis is perpendicular to the plane, we'll draw that in right there, and that would be the y component of mg, and then my x component would run right there. Okay, so I do have to break that one into pieces. I've got a little right angle right here, and it's a nice little right triangle, so I can still use sine and cosine on it. Here is the way to do that. If the hill is tilted at angle theta, this angle right here will always be that same angle. If this, for example, is a 20-degree angle, then this will be a 20-degree angle. All right, and I can do a little jiffy proof here if you want. If this is theta, and over here I've got a 90-degree angle, you know that that triangle has 180 degrees in it. If 90 of it is right there, I subtract off the 90. These two have to be complementary. They have to add to 90. So this one is necessarily 90 minus theta. And then to get this right angle, which, I don't know, right there. It's better on the other side, but I don't think I can get it over there. Yeah, there we go. If that's 90 minus theta, I need to add something to 90 minus theta to get me theta. All right? So, I mean, to get me 90. So this would have to be theta again. This angle right there and that angle right there will always be the same. And generally, they'll just come in here and say a 20-degree hill, something like that, a ramp or inclined plane or something. And so you know this is already 20 degrees. All right? If that's my angle of interest, then straight across would be the opposite, and right next to it would be the adjacent. So you got to be careful which trig function you use here. This is the hypotenuse. This is the opposite. Hypotenuse and opposite is sine. So this would be the hypotenuse, mg, times the sine of theta. Anytime you want this little piece right here, the magnitude of that would be mg sine theta, and it's going to point directly downhill. Now, the reason that that's important is because that arrow, the x component of mg, points downhill. So I've got a little name that I call this. I don't know what other people call it, but I'm going to call that the downhill pull. It points downhill. That little thing right there, mg sine theta, is the reason that things slide downhill. Is the reason that water runs downhill. It's the reason that balls roll downhill, because gravity is pulling on it. It's not pulling mg. It pulls mg straight down. But the steeper that angle gets, then the bigger sine theta gets, and I approach mg. Okay? That's an important thing that comes out of this inclined plane problem. If you see any kind of thing on a hill, you need to point an arrow downhill and write mg sine theta on it. Always and forever. All right? Now what about the y component right here? We said that was the adjacent, and mg is the hypotenuse. The trig function with adjacent and hypotenuse, of course, would be cosine. So the magnitude of this is mg cosine theta. And an interesting thing happens with that we're not really quite ready to use, but I'm gonna halfway cook it up here, and we'll use the rest of it in the next video, okay? If I think about the y direction, here's my box like this. I've got the normal force pointing up, and now I've got this y component of the weight. It's not the entire weight, it's just the y component. And we said that that's going to be equal to mg cosine theta, like that. If I go and sum the forces in the y direction, set that equal to the mass times the acceleration in the y direction, then an interesting thing happens again. The normal force minus mg cosine theta equals, that box's acceleration is 0. It's not blasting up into the air, it's not sinking into the ramp, so I could solve this for the normal force, and it's going to be equal to mg cosine theta. All right? We're going to need that in a little bit. On the next video, we're going to talk about friction. In order to calculate the friction, you got to know the normal force, and now we know it on an inclined plane. All right? So kind of hold on to that, and we'll come back to it in just a little bit. All right? But this is really important right now, and this will become a useful thing right there. All right? So what I'd like to do here is to kind of summarize these, and I'm going to call this the first thing that we need to know here. Let's just call it the DHP for short, downhill pull. Any kind of object on a ramp, on a hill, on an inclined plane, I draw the box, and I need to draw an arrow that points downhill, and that's my DHP. The DHP is always going to be mg sine theta, where theta is the angle of inclination, this angle right here. Okay? So that's the part that we really need for today. Just go ahead and draw that arrow every time you see something on a hill. That's got to be there. All right, let me show you some problems that work like this. Here's a little problem. The truck is parked on a 12-degree hill. Find, oh, I can't do that problem yet because I haven't told you about friction yet. Okay. Well, let me change that a little bit. Let's change truck to ball, and I'll just scratch out parked, and instead of minimum coefficient of friction, I don't know what I was thinking there. We haven't talked about friction. Find the acceleration. We could do that. Remember how we said that balls like to roll downhill? I guess I could spell the word ball right. Okay. So there we have it. A ball is on a 12-degree hill. Find the acceleration. So I'm going to come over here, and I'm going to draw a force diagram. If I can find the cursor for my pencil. Oh, it's way over here on my other screen. Okay. So here's my hill. I got 12 degrees right there. And all I really have to do is say there's the ball, and I've got a downhill pull on that ball. Okay. I don't need to draw the gravity and break it apart. We've already done that. I don't need to draw the normal force. It's all okay. All right. I draw that downhill pull, and we're ready to go. I can come in here and say the sum of the forces equals the mass times the acceleration. And the only force in my force diagram is the downhill pull. Let's think about our directions here and what should be positive and negative. My direction of motion is that way. I always like to call the direction of motion positive. It just makes life easy. So the downhill pull is in the direction of motion. That's going to be a positive force, and that's the only one I have. So I'm going to put in a plus sign right there. And then right here I've got equals m times a. And that's my equation. I can fill in the gap here that I know that the downhill pull is mg sine theta because it's always that. I draw the downhill arrow and it's always mg sine theta. So we've got that. And on the right hand side I've got equals ma. They didn't give me the mass of the ball, but it's okay because I've got m here and m there. So the m on the right is going to cancel the m on the left. Those two go away. Go away. Go away. There we go. Okay? And the acceleration is going to be equal to g times the sine of theta, 9.8 meters per second squared times the sine of the angle. The angle, we know that, it's 12 degrees. Oh boy, 12 degrees. That's going to be the acceleration. I pull up the thing here, and 9.8 sine 12 gives me a 2.04 meters per second squared. Okay? So that's that one. Again, it just makes life a whole lot easier. Just point an arrow downhill, call it mg sine theta. Now, balls do something a little bit funny, so it'd probably be better to say this is a box right here. There's really a little bit more physics involved with a rolling object. We've got to consider something called the moment of inertia and all that. So we'll get to that. Let's put a box instead of a ball, just to keep all the people happy. Okay, a box. That's better. All right, next problem. Find the angle a roller ramp should be run from the back of a truck so that A equals 0.2 meters per second squared. This one's fine. We can do this. There's no friction in it. All right. We can come back on the next video and do this problem again when we do have friction, but right now there's not any, so we're not worried about it. So I'd like you to picture here's a big tractor trailer backed up, and they don't have a loading ramp, so they've just run a ramp down here like this. They're going to put a box on that ramp. There's little rollers all the way down, so that box is going to move this way. That would be the direction of motion. So I'm drawing now my coordinate system, and it's going to be positive downhill. All right, and I need to think about the forces on that box, and I could just go crazy. I could say, well, the gravity pulls down and the normal force is perpendicular and all that. But nothing is happening this way, and nothing is happening this way. The only direction that anything interesting is happening is parallel to the ramp. So I want the forces that run parallel to the ramp. We've already taken these two right here, the normal force and the weight, and broken them up into pieces. We got the components, and I don't need to draw these unless there's a guy pushing down on the box or lifting up on the box, something like that. All right? The only force I need to draw right here would be the downhill pull. I just come in like that. All right? We've already taken care of those other two. In fact, the downhill pull is part of this one, and the other part of that we said we'll use on the next video, so I don't need that. And the normal force was the same way. That's for friction. We don't need that right here because it says no friction. All right? And I come in here and I say that the sum of the forces equals mass times acceleration. Every problem, you want to draw the box, draw the arrows, sum the forces, set it equal to mass times acceleration. There's only one. It's the downhill pull. And right here I have mass times acceleration. The downhill pull is always mg sine theta. So that's equal to ma. And the mass on the right cancels the mass on the left. There's my acceleration. And I happen to know the acceleration. I want that box to speed up a little bit, but not too much. Maybe I'm unloading china, you know, and I needed to get to the bottom and get the job done and off to the next site, but I don't want it to go too fast and break all the china or something. So I want to solve this thing for theta. What kind of angle do I need to put on that ramp to make this happen? Well, if I divide through by g, a over g, okay, and I'm again trying to solve for theta, so I need to get rid of the sine right there, and I can come through and say the arc sine of a over g. That's going to be the arc sine of 0.2 meter per second squared divided by 9.8 meters per second squared, like so. And my calculator knows the answer to that one. Second sine 0.2 divided by 9.8. I need about a 1.2 degree angle, not very steep at all. All right. Again, there's no friction here, so any kind of little incline is going to make that thing roll, and then the more I tilt it, the faster it's going to go. But I don't want it to go very fast, so I need a small angle on that thing. You could set up conveyor belts all over a factory, or a roller coaster. Maybe you're trying to build a roller coaster, you know, and you know how what kind of acceleration you want the cart to go at, and you could design the whole thing out like that. All right. Let's see. Here's one right here. This is kind of the classical inclined plane problem. We're good for this one, so I'm going to go ahead and put it on here. What we have here is a block on a ramp, so I'm going to draw that first. I got a little bit extreme with my ramp here. That's tilted up more than it needs to be, but that's okay. 22 degree angle right there. Actually, that might, whatever. We know the mass of this one. There's a 4 kilogram mass sitting right there. That is the block on the ramp. It says it's pulled uphill by a 10 kilogram hanging mass. Now, when they say that, what they mean is that there's a rope that runs over a pulley and back down, and then I've got a second box over here. I've got a second object like that, and they tell me that this one is 10 kilograms, and you can already see I've got mass and mass, so that's going to get messy, isn't it? Let's call one of them mass 1. I'll try to get that in there, and this one right here can be mass 2. And that little index there, that little subscript, will kind of keep us straight on which mass we're talking about, because there are 2 different numbers. Now, I have 2 masses, and I think I said last time that there were some assumptions that we make every time we have strings and pulleys. If I didn't, let me do that real quick. Strings don't stretch. And have no mass. Okay, and this is always the case for us. We also said that pulleys have no friction. I'll just put no mass, no friction. Okay, so I'm still playing with those rules right there. If the string had mass, if this was a big cable or a heavy chain or something, I'd have to do some more work. If the pulley had friction, I'd have to do some more work. All right, but we're assuming perfect strings, perfect pulleys, and I don't need to worry about that. And that'll be true for everything that we do in here, okay? That's higher level stuff when you start putting all that in. We don't want to mess with that. So, but what I need to do is to draw all my forces in there. So let me come back over here and see what's going on here. We're pulling this red box uphill. The string is doing that for us. The string pulls the box uphill, so I need to draw that. But it's on a ramp, so I need to draw a downhill arrow and call that the DHP. Okay, now again, we haven't done friction yet, so I'm not putting that in. but that would be a potential force you'd have to deal with. Any other forces that are going on in the problem, if there's a guy pushing, if there's a motor, if there's wind, whatever, you could put that in as an uphill arrow or a downhill arrow or whatever direction it points in. But for this problem, that's all I've got on the red box. There's those two forces. The string is pulling it uphill, and gravity, a component of gravity, is trying to slide it downhill. So I'm going to write T minus DHP. And that's my equation. I picked that coordinate system because the red box is moving uphill. My direction of motion is uphill. So I'm going to call uphill positive. That makes the T positive and the DHP negative. And that's the reason I've built it here like it is. I just want to add up all the forces. There are two. One's uphill, the direction of motion, one's downhill. Just like that. Okay? And then I can come in here and say, well, I know that the DHP is mg sine theta. And actually, let me write that a little bit differently. I probably should write m1 g sine theta. I don't want to get it tangled up with m2. And this is m1 also. I'm building an equation for box 1, for mass 1. And you can see that, it wouldn't hurt to put it right here and right there. Okay, but I'm just thinking about the red box. I'm zoomed in right here, and I don't care about the blue box. I don't care about the pulley. I don't care about the moons of Jupiter going around. Nothing else matters. I'm thinking about that box and the forces on it. So I end up with that equation right there. And some of those numbers I have. So let's fill in what we do have. Not T. This is a 4 kilogram. Here's 9.8. Here's the sine of 22 degrees. And over here I've got 4 times A. Like that. I can't do anything except punch up that middle stuff right there. So let's see what we got. I'm going to take the negative 4 times 9.8 times the sine of 22 degrees, and that's a negative 14.7. All right, so about as simple as I can make this thing right here. It's T minus 14.7 equals 4A. Let's put a little box around, a little circle around that for the moment, because that's about as simple as we can get that thing. And notice I can't solve it. There's two unknowns, T and A. I can't solve that equation. It's right. It's correct. Uphill positive, downhill negative. I got, but there's two unknowns, so I can't do anything. When you get to that point, you need to go build another equation. If you've got two unknowns, you got to have two equations. So now it's time to come in here and say, what's going on with mass 2? And I want to sum the forces on mass 2. Set that equal to m2a. Well, in order to do that, you got to know what the forces are. So you draw a force diagram. Say, here's my 10 kilograms. Gravity is pulling straight down, and the string is pulling up. Now, I think we talked about that string last time. If I were to reach up there and cut that piece of string, if I do the scissor test on it, then that box is going to fall. The string is holding it back. It's keeping it from going into free fall. So that's an upward force. I want to set up a coordinate system. I notice that this box is going down. As this one slides uphill, this one's going to go down. So my direction of motion is down. And I've got to tie my coordinate systems together. The direction of motion needs to be positive for both boxes. So when I do this thing, the T is actually in the negative direction, and the M2G is in the positive direction, and that's equal to M2A, like that. Okay? I'm going to fill in the numbers. Negative T plus 10 times 9.8 equals 10 times A. All I can do is multiply 10 times 9.8. So that is going to be plus 98. That's equal to 10A. Two unknowns. I can't solve it. I'm stuck again. So this is where I want to come in and do that stack and add thing. Somehow I need to solve those simultaneous equations. The elimination method is generally your best choice, especially on these easy ones that only have 2 boxes. If you have 7 or 8 or 15 boxes that are all moving, tied together, then you may want to think about using a matrix. But this one's pretty straightforward. You get your 2 equations, you draw a line, you add straight down. T minus T is 0. Those cancel each other. If they don't cancel each other, you set it up wrong. So go do it again. The T's have got to cancel out. And this T right here pulls in the direction of motion. This T pulls opposite the direction of motion. The T's better go away, otherwise you goofed it. Okay, right here I've got a negative 14.7 and a positive 98. Putting those together, I get an 83.3. Adding straight down, 14a. So I need to divide both sides by 14, and that would be a 5.95. That is my acceleration. So I know to put the units, meter per second squared, back on. I've gotten kind of sloppy here. This test usually I do. Everything's in kilograms. Everything's in meters per second squared. If they weren't, then you'd want to fix that up front. Okay, but they are. So we have completed the first part of this. We found the acceleration. They'd also like to know the tension. In order to get the tension, that's pretty easy, because now that I know the acceleration, I could plug it in to the blue equation or to the red equation. It makes no difference. You'll get the same answer either time. Me personally, I don't like that negative sign in front of the T. And if I choose the red equation, I don't have to deal with that, changing the sign at the end, whatever. So I'd probably go T, here's minus 14.7 equals 4 times A, which was 5.95. And I'm going to go ahead and add 14.7 to both sides. So that would be a positive 14.7 plus 4 times 5.95. And I get a 38.5. That is a tension, that is a force, so that should be measured in newtons. All right. And now we've accomplished both of these things right here. I think that's the last, yeah, that's the last problem there. All right. The big takeaway here, you see something on a hill, you need to point a downhill arrow and call it mg sine theta. That's the inclined plane problem. Thank you very much.